Okay, so hope you can all hear me. So let's get started with the class then. So last time we were talking about BCS pairing and superconductivity in the TJ model. So we took a lattice point of view where you had some electrons with nearest neighbor exchange interactions, which were antiferromagnetic. And then we paired the electrons on the bonds because that's the interaction was just nearest neighbor. And from that obtained the usual Poglia-Bob Hamiltonian and all the self-consistency conditions. So what we found from that approach was that there were two different pairing amplitudes now. Initially, the BCS there was just one number, the gap parameter delta, but now we had a delta X for pairing on the X bond and delta Y for pairing on the Y bond. And from symmetry, if you don't break square lattice symmetry, you're only required that delta X and delta Y have the same magnitude, but they can have different phases without actually physically breaking any symmetry. So there's two different choices you're left over. If you also don't want to break time reversal symmetry, which is delta X equals delta Y, or delta X equals minus delta Y. And it wasn't at all clear from the Poglia-Bob equations which is the right choice. In fact, some of the earlier papers made the wrong choice and assumed it was that way, but it turns out that's not the right choice, as experiments show on the cuprates. So I just want to conclude this chapter by giving an alternative point of view to this pairing by thinking about things in momentum space. And in momentum space, there is kind of weak coupling argument, which is not necessarily related to the Hubbard model, which actually relates the shape of the Fermi surface. That becomes a very important consideration and give you some idea of what kind of pairing is preferred. So we imagine that we are dealing with some electronic system. Normally, we just have the Coulomb interaction here in the electron-electron part of the Hamiltonian. But we put in some general interaction, which also depends on the spin indices. So, of course, the whole system should have spin rotation invariant. And so one of the possible form of V alpha beta gamma delta is just spin dot spin interaction with a coefficient which could in general depend on Q, which is called J of Q. So here the idea is this is not a bare interaction, but the idea is you're doing some kind of renormalization calculation. You have some complicated system of electrons with only Coulomb interactions. But once you get rid of a lot of high energy excitations, as we explicitly did for the Hubbard model, you end up with some low energy theory, which has an effective interaction, which we won't, which we're just going to write as some general function, J of Q over here. And the point of view many people often take is that this is some spin dot spin interactions. So maybe I can, instead of computing it, I can measure it. I can go in and do a neutron scattering experiment and measure the spin-spin correlation function of the electrons in the normal state. And from that deduce, and then compute the spin-spin correlation in some RPA theory. And so you match the experiments with the RPA ladder diagram theory, and then you read off from the experiment what is J of Q. Okay, so that's another reasonable strategy for addressing what's going on as far as superconductivity is concerned. But if you took our TJ model as written on the lattice, then J of Q is exactly this. So everything we did last time is completely equivalent to taking J of Q equal to this, except now we're working in momentum space rather than real space. So what we notice about this this J of Q is that it's very large. It's of course positive for Q close to 0, and negative for Q close to pi pi. So in general, we can assume that the important part of J of Q in the real experiment, not in the radiation Hubbard model, J of Q, mod J of Q is large and negative. Well, I didn't write that properly. Mod J Q is large and has a negative, well, mod J of Q is always positive, so I haven't written that right properly. Oh gosh. And J of Q is less than 0 for Q close to, we'll take the wave vector pi pi. So this pi pi is the antiferromagnetic ordering wave vector, where the spins point in opposite direction on the two sublattices. And that's what you see in the experiments. In the experiment, you measure J of Q, and you'll find that it's you have antiferromagnetic spin correlations. So J of Q, well, sorry, am I saying this right? Yeah, J of Q is it's the chi of Q that's very large, but J of Q we're going to take to be large and negative for Q less than pi pi. Okay. But in this particular form written here, it has the same magnitude at near 0. So where it's equal to the maximum value when both Q and Qx and Qy equals to 0, or it has the most negative value in Qx and Qy is close to pi. Okay. All right, so now we just take this interaction and now we have to worry about, is it attractive? We have to ask, which channel is it attractive? And what does that imply? So this is the kind of reasoning people go through. So now, so as written, if I just ignore all the indices, it looks repulsive when J of Q is positive, and it looks attractive when JQ is negative. Okay, so there's a lot of signs to keep track of here, but let's just see how that works. So now I take this, and now I put the sigma dot sigma, and I do a BCS pairing. So when I do a BCS pairing, I'm going to pair the C dagger with C dagger, and I'm going to get some Bogoliubov Hamiltonian. So I'm dropping the momentum indices here. I'm going to look at average value of C dagger alpha gamma. So I'm going to assume that it's spin singlet pairing. So spin singlet pairing means that alpha and gamma have to be opposite and anti-symmetric under exchange. And so this thing must be proportional to epsilon alpha gamma for spin singlet pairing. So now I put this epsilon alpha gamma in here by pairing these two. Then I have all these indices coming from the spin dot spin. And so I have to evaluate this particular object. Okay, so this is some tensor which only depends on beta and delta, where I'm summing over alpha and gamma. And I've evaluated for you. It's -3 times epsilon beta delta. So that means that the undaggered operators, which will, after you pair these two, this beta and that delta have to be opposite, which is good because that's exactly what you expect for that also to be spin singlet. And there's a -3. So what we've seen is that the sigmas have turned what's attractive to be repulsive and what's repulsive to be attractive, because we have to have opposite spins, essentially. Okay, so now near pi pi, this interaction kind of seems repulsive because of that extra sign. So you might wonder, well, how is that possibly going to lead to pairing? Okay, but you just go ahead and plow ahead and write down the BCS Hamiltonian, the Bogoliubov Hamiltonian, and you obtain a gap equation. So if you go through the procedures that we have worked out, but keep track of the momentum a little more carefully, this is the gap equation you're going to get. Okay, this is exactly the gap equation we had before with a few differences. One is that delta of K, delta depends on momentum K, and the interaction also depends on momentum. And it comes in this kind of interesting way. Delta depends on K, but it's not the K on the both sides. So it's like you have a pair with momentum K. Since the interaction depends on the momentum, you go from momentum K to momentum P. and then you end up with momentum P there. So the interaction is has momentum J of P minus K. So let me try to draw this as a Feynman graph, so you see where this is coming from. I need a little more space. Well, no, I can do it over here. So I have, so this is kind of the picture. You have a Cooper pair moving here, and you have a Cooper pair moving here. I mean, not 2 electrons, so that's Cooper pair. So let's say this is K. So you have these electrons, this has momentum K, and this is minus K. Because delta of K is, represents a Cooper pair, which is, it doesn't have center of mass momentum K. It means that the electrons have momentum K and minus K, and the center of mass momentum is 0. So this pair of electrons then has some interaction J, and it gets scattered in momentum space to some other Cooper pair, which is still 0 center of mass momentum, but say momentum P and minus P. And now to conserve momentum, you see that this exchange interaction should be at momentum K minus P, or the other way around. It's an even function anyway. Now you conserve momentum over here and also over here. And that's why you get the J of K minus P. So really the way you think about this is you have a Fermi surface, you have a pair of electrons on the opposite sides of the Fermi surface, and they keep getting scattered around to different points of the Fermi surface. And the interaction you pick up is the momentum transfer from, say, this point to that point. Okay. All right. So now you look at this and you try to figure out which momenta are important and which will give you most likely a solution to this equation. So the general rule is you want your little k to be on the Fermi surface. So you want your little k to be on the Fermi surface. So if this is your Fermi surface, Ek equals 0. So the k's have to sit on this Fermi surface. I mean, note this is a summation over all k, not just the Fermi surface, but you want k to be on the Fermi surface. So suppose you start out here, and then you're going to scatter by some momentum. Well, what momentum should be scattered by? Well, you want to scatter by a momentum where J is large. Okay, now J, at least the way we wrote it down before, was large at 0, 0. But you know that's a fake, because at 0, 0, then there's also the on-site repulsion, which you've just thrown out anyway, the Hubbard U, which is a very large parameter. So we're not really interested in 0, 0. We're interested in large momentum scattering because that's what's going to help us get around the fact that you don't want the particles to be right at the same point. Because when you take the Fourier transform of a large momentum, you can get oscillations and you can prevent anything happening right at the origin. Okay, so you want this to be some large momentum. And in fact, preferably you want P minus K to be pi pi. Okay, so what you want to do is you want to scatter from somewhere here, for example, to somewhere over there. And then this wave vector from here to here, that's pi pi. Okay, so maybe that's a process that will dominate because you've got electrons near this region and this region on the Fermi surface, and you can then have very large momentum scattering between them. So this has to be pi pi, and this is then near pi 0, and this is near 0 pi. And this is then negative. Okay. Now for this thing to have a solution, what this tells us, the delta over here, let's call this region K, and this is P. So and this is negative for K equals pi pi. So therefore, for this thing to make sense, this delta must have the opposite sign from that. So you must have delta of K will lead to a sensible solution. Okay, so that's precisely, so this means that delta of k must have opposite sign in this direction and to that direction. So in momentum space, the simplest function that can do that and also be periodic in the Brillouin zone is cosine kx minus cosine ky. So that's precisely the pairing that we had for delta of k. If you remember, our delta of k was delta x cosine kx plus delta y cosine ky. And we said that delta x must be opposite sign of delta y. Oops, what happened there? Oh no. Okay, I'll have to fix that later. All right, so that's the answer then. If you have this type of Fermi surface, and most of your scattering is happening at pi pi, then it's D wave that makes sense. If you took an S wave, then near on the Fermi surface, where the Fermi surface is not too far from this point, then you would get actually a repulsive interaction at this wave vector. And you don't want S wave, because then this if delta P and delta K had the same sign as in an S wave solution, then this would have no solution, because the left hand side be positive and the right hand side be negative. So there is no solution. So that's actually the correct reasoning, which gives you some idea what the pairing should be. I guess the name of David Pines is associated for having presented this type of argument in the early days of the cuprates. And then the similar argument was made and also Scalapino, excuse me, was for when the pnictides were discovered. The Fermi surface of the pnictides looks very different from this. It's not just one big electron. So it has got little pockets in different portions of the Brillouin zone. And then if you just try to figure out very analogous reasoning, knowing what the magnetism looks like from neutron scattering, and taking the Fermi surface configurations, you find that extended S is a more reasonable solution there. Okay, so that's pretty much the end of the chapter. Here's another picture of what's going on. Here now, the green is supposed to represent Cooper pairs, which have say positive sign, and the red is supposed to represent Cooper pairs that have negative sign of their pairing amplitude. And so what happens is you go from A and B, 2 electrons here and there, which are forming a Cooper pair, will scatter to points C and D with a J. And then as they scatter, the sign has to change, only with the sign change does the attraction, does the Schrodinger equation for the Cooper pair have a solution. Okay. And this keeps happening over and over again. And that coherent process is what leads to D wave superconductivity. Okay, any questions? I think that's the end of this discussion on Cooper pairing and antiferromagnetism and their connection. So the basic bottom line is that antiferromagnetism likes spin singlet pairing, and that tends to be D wave more often than S wave. And then if you had ferromagnetism in the material, then you tend to end up getting spin triplet pairing, which tends to be P wave. And that's what happens in helium-3. Liquid helium-3 is a Fermi liquid, and when you go to very low temperatures, millikelvin temperatures, it becomes a superfluid, and is believed it's some form of P wave pairing. I mean, it's not believed; it's pretty well understood, and that's connected to ferromagnetic spin correlations in helium-3. And if you were at the March meeting and there was a talk by Pablo, there was some indication of P-wave pairing or triplet pairing in twisted bilayer graphene, and it may well be connected to some kind of ferromagnetic spin polarizations. But that's, of course, very much a topic of debate and study these days. All right, any questions then before I close this chapter? Let me also say I put on Slack some list of possible topics for your presentations. If you start thinking about presentation, just send me an email of what your ideas are. If you need some advice, or talk to Ryan or Darshan. And then once we have agreed to something, I'll list it on the course website so other people know that you're covering that topic. And I mean, in principle, we can have more than one talk on the same topic, but it'll be a better use of your time if it was all on different topics, because I hope you'll attend the talks, the presentations by your classmates, and I think you'll find that very useful. And that's really the purpose of it all, so that you can all learn some other stuff other than the standard topics. Okay, so the next chapter I want to cover now is Fermi liquid theory. After this, as you see from the syllabus, we'll talk about the Kondo effect and the Kondo lattice models, and then a bit about disordered metals, and then finally theories of non-Fermi liquids. So since we're going to talk about non-Fermi liquids, we better understand what are Fermi liquids to begin with, and that's what we're going to talk about today. So Fermi liquid theory is just a formalization of everything we've learned using Hartree-Fock theory. And from Hartree-Fock theory, we learned about that actually the perturbative computation from the free electron gas didn't change very much. It gave you still, it seemed like you had a Fermi surface, and then there was some renormalization of the particle, the quasi-particle dispersion near the Fermi surface a little bit. There seemed to be some dramatic effects of long-range Coulomb interactions, but we found that once you accounted for screening, most of those dramatic effects went away. And the main residue of it was a plasmon excitation at very high energy. But let's say we're not interested in such high energies like the plasmons, and we just want to focus on the low energy properties of a metal. Then it seemed like free electron theory is not a bad starting point. The only thing you won't get right is the Fermi velocity, exactly right. And that's basically correct. But we want to see if we can do better than perturbation theory, and that's what the Fermi liquid theory is about. It's a formalization which allows you to make a bunch of exact statements. So these are exact statements. The flavor of these exact statements are, of course, we can't compute everything from first principles. That's too hard. Just knowing nothing but the electron charge or something, I can't compute all the properties or the value of RS. But perhaps I can state that the low energy properties are just depend on a few numbers. And from those numbers, I can predict many different experimental observables. For this to be useful, of course, the number of observables should be greater than the number of fitting parameters, or the number that characterize the low energy theory. And that is indeed the case, and that's what Fermi liquid theory is. It's sort of a kind of thing that we do very often when you're doing classical stat mech, or thermodynamics. We say, okay, of course, we have some very complicated system, but for that complicated interacting system, we can reduce everything to some equation of state. And once we know the equation of state and a few parameters like the viscosity and the thermal conductivity, we can predict all kinds of things. So we want to do the same thing now, but for a quantum state at 0 temperature. So it's the analog of hydrodynamics and thermodynamics, but for a quantum system, where we have to really think in terms of coherent excitations and their dispersions. So it's the overall philosophy is similar, but the actual physics is very different. Okay, so that is provided by Landau's Fermi liquid theory, so I'll first kind of give you a presentation of the principles of Landau Fermi liquid theory, and then relate it to everything we've learned so far using Green's functions and diagrams. But it's possible to present the argument without even knowing anything about Green's functions, just by almost pure thought, just thinking a little bit about what it means to have a many-body interacting system which has a Fermi surface in some non-perturbative, well, in some exact way. Also, another remark is I know some of you have already taken 268R last semester, where we covered superconductivity and also Fermi liquid theory. But let me say that even though there is some overlap, of course, with what I talked about last semester, but let me say that the rest of the course, after we're done with Fermi liquid theory, will be totally new things that we didn't cover last semester. Okay, so first let's just recall some basic properties of the free electron gas. So suppose I have free electrons. In fact, in general, I try to keep this as general as possible. They don't have to be moving in a uniform positive background. The Jellium model. So in the Jellium model, the dispersion would be this. But let's imagine there's some general E of P for free electrons. Could be any function of P. Notice importantly, however, I've absorbed the chemical potential in the definition of EP. So then the Hamiltonian in the grand canonical space is just free electrons, and I've even put the spin index, although soon I'll just drop it because that makes the equations more complicated. So what is the ground state of this Hamiltonian? Well, you just fill up all the negative energy state. That's the lowest energy state for a given chemical potential. So this is the ground state. And so what we see that immediately this defines the Fermi surface, which is the boundary between the occupied and empty states. And the equation of the Fermi surface is just EP equals 0. So you have one conditions, and so the surface is D minus 1 dimensional, where D is your space dimension. So in 2 dimension, it's just a line. We still call it a surface. Okay, so that's the ground state. What are the excitations? Well, the excitations is you can add a particle, but you can only add the particle outside the Fermi surface, or you can remove a particle, and then you can only do that inside the Fermi surface. And what is the change in energy of this Hamiltonian? The change in energy of this Hamiltonian, when you add a particle, is just EP. And when you remove a particle, it's minus EP. But fortunately, you're removing a particle for EP that has negative energy. So the excitation energy is just always EP, modulus of EP. So if I plot the excitation energy, so this is P along some direction in momentum space. This is the excitation. Then it looks something like this. So this is mod EP. And these excitations above the Fermi surface are particles. So they have charge +1. And these excitations below the Fermi surface are holes which have charge -1 in units where the electron has charge 1. Okay. And EP itself, it's interesting to draw EP, is a smooth function. Okay, so this is EP. So, focusing on the actual excitation energy is a bit confusing. Of course, excitation energy by definition has to be positive, but then you get a function that's non-analytic. And whereas you know that in the underlying theory, so EP is some smooth function, there's nothing bizarre happening to EP at PF. It's just some PF could be any point in momentum space. So this is the momentum PF. And there's no singularity EP at PF. But there is a singularity, the excitation energy at PF. Okay, so that's a subtle point that Landau's Fermi liquid theory deals with in a kind of a clever way, which I will describe in a minute. So these excitations are what you call the elementary excitations, because they just, from these excitations, you can build all the other excitations. So that's the basic idea. There are many types of excitations, but it's useful to think about some of the other excitations as made up of simpler excitations. So you compose the elementary excitations to create other excitations. And that's basically, if you wish, the definition of a quasi-particle. Quasi-particle is an excitation which can be composed to get other excitations. So you can take any number of these quasi-particles. So sometimes quasi-particles includes quasi-holes in their definition, and just add them up. So you take a bunch of p's and you just add up this, and that gives you some multi-particle excitation. Could be the particle-hole continuum. It could be a Cooper 2-electron, the particle-particle continuum, Cooper pairs, whatever. But they're here right now, they're non-interacting, so the energy is just the sum. All right, so that's very trivial statements about the free electron gas. Let's continue to the interacting electron gas. So the basic assumption is adiabatic continuity, but even that is kind of subtle. But for the ground state, it's not very subtle. So we imagine we can tune the strength of the Coulomb interaction and slowly turn the Coulomb interaction on from the free electron theory. So we start with the ground state of the free electron gas. We turn up the Coulomb interaction, and the ground state will change. The wave function will change. But we will assume that as we do this, there's no dramatic phase transition or some superconductivity or magnetism or something appearing. We just go smoothly without any apparent dramatic change from the ground state of the free electron gas to the ground state of the interacting electron gas. Now, you notice I've been a little vague on what I mean by adiabatic. Of course, the word adiabatic normally is a very precise definition, but it's precise in systems that have an energy gap. Suppose you have a ground state here and the first excited state has a gap. So that gives you some energy gap, Eg. And when you make an adiabatic change, it just means that the rate of change is much smaller than the energy gap divided by h bar. So the energy gap gives you a scale, and you just assume that nothing, and you just go from one energy gap to the other, and the energy gap doesn't close anywhere in between. So then the whole adiabatic process is completely rigorous. Here, this is not a system with an energy gap. You can see right here at PF, we have 0 energy excitations. So that's why I have to be a little, it's a little wishy-washy, but okay. Let's assume that somehow in some reasonably well-defined sense, there's adiabatic continuity. Okay, so we just say that the ground state G evolves smoothly to the unknown ground state of the electron gas. Okay, so now let's do this not just to the ground state, but to the excited states. Let's do it for the elementary excitations. Now for the case of gellium, here again, it's very clear. So you create one elementary excitation, so that you have an excitation. There's some very low energy excitation here in the free electron gas with some momentum P and charge plus C. And now you just assume that as you do the adiabatic continuity, it goes into some excitation of the interacting electron gas, which, because you're conserving momentum in the whole process, should be an elementary excitation of the interacting electron gas with momentum P and the same spin. So that, if you wish, formally just tells you your definition of quasi-particles. And then you also have your quasi-holes, which are then has to, by definition, have momentum minus P. So this tells you, if I believe this adiabatic continuity argument, that even the interacting electron gas has a Fermi surface, because the Fermi surface now is the boundary which in momentum space, which separates elementary excitations which have charge +1 to those which have charge -1. So inside the Fermi surface, there's some complicated elementary excitation, which has charge -1, and outside it has charge +1. And so I have perfectly well defined what a Fermi surface is. I've even defined what my quasi-particles are, my elementary excitations are. They're just adiabatically connected to the quasi-particles or the excitations of the free electron gas. Okay, that's an argument often stated in books, but and it's correct for Jellium, but it runs into some trouble even for once you put in any lattice. Because what can happen once you have a lattice, and this is not a small effect, is that the Fermi surface can change its shape. There's no guarantee the Fermi surface should have the same shape for the interacting electron gas as it has for the free electron gas. And so then how do you account for this? So, all right, so this is where the non-rigorous part comes in already. Okay, what we're going to show by the end of this chapter is that while the Fermi surface can change shape, it cannot change its volume. It can start changing its shape, but it's like an incompressible sphere. It can change its shape, but it always encloses the same volume. And that's called the Lettinger theorem, which we'll prove by the end of this chapter. Probably not today, but I think next lecture. All right, so anyway, so for the interacting electron gas, we say that, so we cannot assume that EP is only a function of mod P, so the Fermi surface can change shape. But the volume enclosed by the Fermi surface is an adiabatic invariant. That's the Lettinger theorem. And today we also understand it, similar to other invariants of many-body systems, like the quantized Hall conductance and other topological invariants. There's some connection to that, which maybe one of you could cover in your presentation, but I won't talk about here. Okay. So in the presence of a lattice, our basic assumption is that there is a smooth function EP. So there's still a sense of a Fermi surface, which is EP equals 0. And there's some in the many-body system, some surface, so that the excitation energies are quasi-particles on one side of the surface. Excitation are quasi-particles with charge +1 on one side of the surface, and quasi-holes with charge -1 on the other side of the surface. And this EP is still a smooth function of P. There's no singularity in EP at the Fermi surface. So these are assumptions, and really the only way you can verify these assumptions is to prove them in perturbation theory. So then you have to, open up your Green's function technology and see that this is true every order by order in perturbation theory. So I'm going to avoid that for a bit. So let's say this is a postulate that in the interacting system there's some function of P, which I don't know. I don't know how to compute it. I could measure it in an experiment. And that function E of P defines the Fermi surface, just the line EP equals 0. In fact, we'll be only interested in low energy excitations near the Fermi surface. So we can expand EP to linear order in the momentum. So we have some Fermi surface, So here's a momentum space. So this is Px and Py. And you have a little piece of Fermi surface here. It can have any shape you want. This is the point P0. And there's a normal to the surface, which we call N. So since the Fermi surface, by definition, is an equal energy contour, so the Fermi surface is the contour EP equals 0. So EP is constant. In fact, it's equal to 0 on that line. And this means that if I expand EP from this point P0, EP only depends upon this coordinate, normal to the surface. And that's this statement right here. EP is P minus P0 dotted into N. And this coefficient is what we call the Fermi velocity. which is the absolute value of the gradient of grade EP. And if you say the mod of P naught is PF, then the effective mass is defined by this equation. Okay, so given an EP, at every point P naught, I can read off a value of PF. I can read off a value of VF and M star. Now, in a general lattice, this value will be different at every point of the Fermi surface. So it'll depend on the direction, assuming this is a simple closed surface. In Gellium, of course, these are just numbers. There's only one number PF. In fact, it'll equal to the PF of the non-interacting gas by adiabatic continuity. And there's just one number M star, which is related to VF. But for a general lattice, you need an infinite set of numbers, one for every point on the Fermi surface. Okay, so that's our postulate for the interacting electron gas, which you can verify in perturbation theory using Green's function. That's what the low energy excitations look like. And now we make a further assumption. And this is really the key assumption, the stronger assumption. The further assumption is just like in the free electron gas, you could build up the multiple energy excitations, the higher excitations from the elementary excitations. You could just compose them to get many other excitations by taking more than one excitation, because these are kind of independent excitations which don't feel each other very much. In fact, here they don't feel each other at all. So here we're going to say the same thing, that the other excitations can also be obtained by composing the elementary excitation. So we assume that's also true in a strongly interacting system. So this is a very strong assumption, because if you just think in terms of how many such excitations you have, so if you have a system of size n, the number of elementary excitations is the number of momenta, which is really a number of order n. You know, when you put the system in a box, the momenta has a discreteness, which is 1 over the length of the box. So the total number of momenta typically are of order n, where you're measuring n, units of the lattice spacing, the size of the box in units of the lattice spacing. But the number of composite excitations is very large. It's e to the n, because any given elementary excitation can be either occupied or not. And so the total number of possibilities roughly is 2 to the n, because depending on whether you pick or not a given elementary excitations. So the number of composite excitations is huge. And we are assuming that all these huge excitations can also be thought of as composites of these elementary excitations for an interacting electron gas. And the interactions could, in principle, be extremely strong. They're only requiring some sort of continuity to zero interaction. But we could go to very strong interaction without encountering any singularity. Okay. So so those are assumptions, but now comes, so what are we going to get from all this work and all these assumptions? After assumptions, we finally have to make some predictions. So the prediction in the free electron gas was very simple about these many electrons of these multiparticle excitations, that the energy of a multiparticle excitation is just the sum of the energies of the particles. Okay, it turns out this is not true anymore. So it's not that they're not entirely independent of each other, and the energy is not exactly the sum, even at very low temperatures. So we're going to assume that we are at very low temperature, so we're looking only very low energies near the Fermi surface, where EP is very small, and we're composing multiparticle excitations out of them. But even then, you might think, well, these are all very dilute and at low temperatures, and you can move them far apart, and therefore they should just add the energies. Turns out that's not true, because these are really plane waves, and they're going to start to feel each other. You can't really localize them in space. But so then you might start getting worried, how is this any useful if these composite excitations interacting, the elementary excitations are all interacting with each other in the composite excitation. So what Landau showed was that you can account for these excitations exactly just by introducing another set of parameters, which are called the Landau parameters, which I'm now going to introduce. Okay, but before I get there, I have to account for this technical issue, which is that I don't want to talk in terms of excitations because I don't want to keep track of this mod epsilon p everywhere. This mod epsilon p introduces a singularity that wasn't there because there's no singularity in the dispersion right at the Fermi surface. The Fermi surface only depends on the density. It can move around as you change the density. Okay, so the way we get around it is by a mathematical trick. And when I was learning this and reading many books, it wasn't made clear that this is a mathematical trick. It seemed like a physical assumption, but it's not. So there's no physics assumption. It's just a bookkeeping device. So what we're going to say is the following. Since we don't want to keep track of whether an excitation is a whole or a particle, everything is going to be a particle. So to do that, we want to, first of all, make a postulate about the ground state. So the ground state wave function, I don't know what it is. It's some very complicated wave function. And these quasi-particles and quasi-holes are only defined very close to the Fermi surface. So when I'm very far from the Fermi surface, I don't know what the ground state particles and holes there look like, and what the particle hole excitations look like, or anything about the ground state in general. But let's just make a postulate that we're going to introduce a fictitious ground state, which I'm just going to view as made up of quasi-particles, just like the free electron ground state was made up of bare particles. So there's this momentum distribution function, which I'm going to draw here. This is P, and this is the number of particles or quasi-particles with momentum P. I call it N0 of P. Here's the Fermi momentum along some direction. And now I'm going to say that N0 of P is just a very simple function. It's a step function from 1 to 0. Okay, oops. Okay. So this is exactly what N of P, which, this is equal to, very carefully say this, N0 of P is just the expectation value of C dagger P, Cp for the free electron case. Okay, so I'm just going to postulate that there is some, not a bare particle like the electron, but some renormalized quasi-particle. And that renormalized quasi-particle is such that I can define some operator for the renormalized quasi-particle even away from the Fermi surface, such that N0 of P for the quasi-particles also has exactly the same form as the free electron gas has for the particles. And I'm going to get away with this definition because when I actually apply the theory, I'll only be interested in changes in quasi-particle number right near the Fermi level. I'll be only interested in this region. So if I'm only interested in this region, this is actually a reasonable description of what happens in an interacting electron gas, because there you're just removing and adding these quasi-particles to create multi-particle excitations. And so what I do over here shouldn't matter much because I'm not going to really look at that region when I finally compute anything. All right, so that's the ultimate justification for it. But it's also a very convenient bookkeeping device, because now what I can say is, now let me define. So I want to characterize some multi-particle excitation, which is made up of both quasi-particles and quasi-holes, but I don't want to keep track of which is inside the Fermi surface, which is outside. I just want the same formalism. So now I define something called delta N of P, which is the distribution of excitations, which is the number of excitation momentum P minus N naught of P, where N naught of P is exactly this function 1, 0. Okay. So now this thing will be positive for particles and will be negative for holes, or will be positive for quasi-particles and negative for quasi-hole excitations. So if I, initially, if you had asked me what is the total energy of the system, I would say the total energy of system is the number of quasi-particles at momentum P, and this will be for P outside Fermi surface times EP. And then I would say it's the number of quasi-holes of minus EP for P inside the Fermi surface. This is the excitation energy. So all I'm doing right now is changing the sign. And all I'm doing then is I'm transferring this sign from here to here. So I'm defining a new density, delta N of P, which is equal to N quasi-particle inside the Fermi surface and equal to N quasi-holes, N quasi-particle outside the Fermi surface and N quasi-hole inside the Fermi surface, but negative. So this minus one has been absorbed into this. So now I can say this is equal to, if I just add the energies, it's equal to sum on P with no restriction of delta N of P times EP. Okay, and this is a much nicer expression now. And to be able to work with this, I needed to fill all the states by quasi-particles inside PF. Okay, and this is what I'm going to work with now. So that was just a clever bookkeeping device, which also works for interacting systems. All right. So let me just finish. So the punchline, however, this is not the full answer. There is another term here. And the reasoning is as follows. So let's try to think about how small this is at a given temperature. So I raise the temperature a little bit. Now, what I expect is that I'm going to get a bunch of quasi-particles and quasi-holes excited at finite temperature T. So there'll be some quasi-holes here and quasi-particles here. And the width of this, where these get excited, will be of order temperature. So that's the typical value of EP. This thing is of order temperature. The next question you can ask is, so delta N is of order 1, either -1 or 1, where they're outside the above the Fermi surface, inside the Fermi surface. And the next question you can ask is, what is the range of momenta? Well, the integral over momenta has the angular coordinate, which is just some surface area, but there's also a radial coordinate. So the range of momenta that you're going to integrate over is also T. So the whole thing together, this also gives you a factor of T. So together, these two combine to give you energy of order T squared. That's something you already knew. If you take a free Fermi gas and just compute how its energy changes, as you raise the temperature, it changes order T squared. All right. But now what Landau pointed out, that there is another term, which also is of order T squared. And this is the Landau interaction term here. There's no EP. So everything here is of order 1, delta N of order 1, delta N of P, and delta N of K of order 1. But there's two momentum integration, each of which will give you a factor of T as you integrate the radial direction. So the whole thing is of order T squared. And then F of P and K then are your Landau parameters. So what this is telling you is that there's another contribution to the energy of the multi-particle excitations of a Fermi surface. So if here's your Fermi surface, then you get some excitations in this region of some density of excitation here with momentum k, and you get some excitation somewhere else with momentum p, and there's an interaction between them, which is f of pk. So the energy of the quasi-particles here will depend upon whether they are quasi-particles over there in a different region of momentum space. So there's this effectively infinite range interaction on the Fermi surface, in large momentum, but that's okay because in real space, it still can come from local interactions after a Fourier transform. And then there's some function, f of p, k. So this is just a set of numbers which are defined for p and k on the Fermi surface only. So that's why I have the hats on them. So it depends on just on the surface coordinates, not on the full momentum p and k. And the dependence on the radial coordinate we ignore because the radial fluctuations are very weak at low temperatures. Now in the jellium, there's also spherical symmetry, and you can decompose the f of p and k into angular momentum components, and which is what you do for helium-3 also, because it's in a continuum. But on a lattice, in principle, there are more complicated functions that you have to figure out. Okay, so that is the complete statement of Landau Fermi liquid theory then, that all the composite excitations of a strongly interacting Fermi gas are characterized by one, a function E of P, which vanishes on the Fermi surface, and two, this function F of P and P hat and K hat, which depends on 2 points on the Fermi surface. And once you give me these properties, at low temperatures, I can compute anything you want. So that's the postulate. And we're going to compute a few things and then see where this postulate comes from using Green's functions also, a little bit, anyway. Okay, questions?
Severe?
Yes.
You mentioned that the radial fluctuation is low in low temperatures. Could you explain why?
Well, so the typical elementary excitation will have energy of order kT. Okay, so if your distance p from the Fermi surface, so this is sorry. So we have some elementary excitation with momentum is q along the Fermi surface, then the energy will be Vfq, and this is of order temperature. So the range of q is of order temperature divided by Vf. So that's the range you're going to integrate over to get any change as you raise the temperature from the ground state. We're not interested in the ground state energy itself. That is just a constant we pull out. We're interested in the change in the energy as we raise the temperature, or we perturb the system a little bit.
I see. So you mean that the fluctuation in the low temperature would be only to the tangent of the sphere that doesn't change the whole, the magnitude of the wave vector?
Well, in general, you have some complicated Fermi surface, okay? And this Fermi surface is the equation EP equals 0. Okay, so you're given a function EP, and this is your Fermi surface. So I have to mute somebody here. I can't tell. Okay, please mute yourself. Okay. Okay, so you have this Fermi surface, and now you're going to create excitations. So the excitations, to begin with, I assume are quasi-particles and quasi-holes. And these quasi-particles and quasi-holes will be near the Fermi surface. So maybe I'll create a quasi-hole here, and maybe a quasi-particle there. So we want to figure out the energy of this quasi-particle. What I got to do is take the normals to the surface. So here, in this case, I'll take a normal in this direction. This is in the direction n. Oops. I'll draw a normal. And that's the distance. This is the distance I'll call Q, and the energy will be the Fermi velocity at that point times Q. The Q is the distance to the the smallest normal from whatever the shape of the Fermi surface is. So that's what Q is. So that's the simple elementary excitation, either a quasi-particle or a quasi-hole. And then when I raise the temperature, I'll get some gas of these quasi-particles and quasi-holes. So I'll assume the thermal state is just made up of a gas of these. So I have some function, delta N of P, which is basically of order 1, it's 1 on this point and wherever the gas may be. But it's delta N of P, the modulus of delta N of P is of order 1, otherwise it's 0, only within T over VF. The P is T over VF only for P within T over VF. Let me write that. P within T over VF of the Fermi surface. So basically this delta N of P is 0. I mean, I'm not going to create a quasi-particle over here, quasi-hole over here, or quasi-particle out there. It just costs too much energy at a given temperature. So all the low energy excitation right near the Fermi surface. So this function delta N of P is 0, except right near the Fermi surface, and delta N of K and this one. So these functions are only defined in the window right next to the Fermi surface in a width of order T. So this is a width of order T, this is a width of order T. The radial integration will give me a factor of T squared. The transverse integration will just give me some factor of the area of the Fermi surface. It's just a constant I pull out front. That just depends. It's like a phase space factor. Here, this is defined on a width of order, is non-zero on a width of order T. But this value of EP is also of order T. So now you're getting a factor of T squared for different reasons. You're getting a factor of T from EP and a factor of T from the integration over P. Here you're getting both factors of T from the integration over P. So it's a little different. F of pk is just some constant. It doesn't vanish on the Fermi surface, whereas EP vanishes on the Fermi surface. So that was Landa's point. Because this EP is vanishing on the Fermi surface, you have to go to quadratic order in delta N to be consistent. Okay. And this is, it really is special to this existence of a surface over which you have to do this integral, and the integral over P effectively becomes one-dimensional, only transfers to the Fermi surface when you're counting energies as the temperature dependence or the response to some external perturbation, which is weak. Okay, I hope you answered the question. Any other questions? All right, great. So I think the homework is due today, and there will be another problem set. I'm not sure when. Ryan's working on it in the next few days. It's kind of a longish problem set, I think. But for now is the time really to start thinking about your presentation, and homeworks will kind of decay away. But you should start working on your presentation. The first step one is to think about what you want to talk about. Okay, so see you. I guess I have a discussion session tomorrow morning at 9 a.m. Is that right? Yeah, I think if I remember right.